Hello everyone, my name is Shenzhu Hen and I am glad to present our demo paper, ADEPT, a testing platform for simulated autonomous driving. Here we list the content of the presentation, including background, motivation, overview, and two methods. In recent years, autonomous driving has received more and more attention. They use many kinds of data from different sensors, such as LiDAR, camera, radar, and GNSS. ADS can be divided into two types, modular pipeline and end-to-end pipeline. ADS testing methods can also be divided into three categories: physical testing, virtual testing, and hardware-in-the-loop testing. In general, they are all trade-offs between authenticity and cost. Our work is based on virtual testing. The motivation of our work is that we want to make virtual testing more realistic and effective. The realistic means testing scenarios should be as close to real life as possible. So testing scenario is necessary to serve as the driving environment of ADS. The effective means the interaction between ADS and the virtual environment should be same as physical testing. The feedbacks and the behavior inputs closed loop is necessary. So we present our platform ADEPT. Here is the overview of our platform. All modules in red boxes are developed by us, while those in blue boxes are from Color or Unreal Engine. The simulator kernel layer includes key components directly built upon Unreal Engine or Color to provide specific operations for ADS testing. The ADS testing libraries layer provides concise interfaces for upper layer. The scenario engine layer implements various methods for effectively generating real-world scenarios that may trigger ADS violations. Currently, there are two methods. The first method is generation of test scenarios for accident reports. The rationale of this method is that we have known that human drivers made mistakes in accidents, and that most ADS learns from human drivers' behaviors. So we surmise that ADS is prone to make mistakes in accident situations. In order to generate test scenarios, we need to solve two challenges: how to get structured data from accident reports in natural language, and how to generate scenarios based on the structured data. To get over the first challenge, we use the GPT-3 to analyze the accident reports and extract key information. Then we generate scenic codes based on the key information. As we can see in the picture, key information from the accident reports is extracted and can be seen in the code. To get over the second challenge, we use Scenic to describe the scenarios and use the tools provided by Scenic to generate scenarios. As we can see in the picture, key information from the accident reports can still be seen in the picture. Next, let's watch a demo video. In report 1, vehicle 1 is driving on the road and vehicle 2 enters the road from the right side, affecting vehicle 1. According to the report, some scenarios meet the description have been generated. In 5 scenarios, ADS only passed 2 safely. In report 2, vehicle 1 is passing the intersection and vehicle 2 also will pass the intersection at a certain time and a collision occurs between the two. In the 5 generated scenarios, ADS also only passed 2 safely. This shows that our scenario generation tool can indeed cause ADS errors more effectively. Now we will talk about the second method, a closed-loop testing based on adversarial attacks. Adversarial attacks reveal the vulnerability of DNNs. However, to ADS, a single perceptual attack like modifying image pixels will pose limited threats. Because ADS has error correction capability and physical factors like lightning and blurring may diminish the effectiveness of attacks. Instead, we believe that closed-loop and robust attacks are needed for the purpose of hijacking the ADS. Now we will talk about the solution to achieve continuous closed-loop attacks. We adopted the attack framework shown in the figure. We choose Billboard as the carrier to counter attacks. As shown in the figure, the sensor data is sent to the ADS and the attacker. The ADS calculates a new controlling decision, causing the vehicle's position change. The attacker generates a new perturbation to modify the billboard. Both of them change the vehicle's environment together, thus changing the sensor data acquisition at the next moment. The attacker also uses the pair pursuit algorithm to adjust the target of counterattack so as to achieve the purpose of hijacking vehicles according to the established trajectory. Now we will talk about the solution to achieve robust adversarial attacks. First, we locate the billboard area in the image, that is our attack area, then obtain the transformed image collections through a series of transformations. Then we calculate the gradients of the optimization target with respect to the input and use mask filtering to obtain the gradients of the attack area. Finally, we use gradients to update the image and continue iterate until the designed effect is reached or the iteration reaches the upper limit. After the attack, we display the pattern of the target area on the billboard on the test platform by a fine transformation. Here is the experiment demonstration of closed-loop testing based on adversarial attacks. In experiment 1, the red circle shows the billboard. The left one is without adversarial attack images, and the right one is with adversarial attack images. And then we compare between the accepted trajectory and the actual trajectory. In experiment 2, we hijack the vehicle to collide with the pedestrian who attempts to avoid the collision. In experiment 3, we show that it is impossible to hijack the vehicle without continuous attacks. Thank you for listening.